You know that moment you click a link and a web page just appears? It feels instant, like magic. But what's really happening is one of the most incredible high-speed journeys on the planet. Today, we're going to pull back the curtain and actually trace the invisible path your data takes across the globe, all in the blink of an eye. Let's dive in.
We're going to break this journey down into 6 key stages. We'll start with how your click becomes code, see how it gets out of your house, learn the rules of the road it has to follow, figure out how it finds its destination, look at the dangers it has to avoid, and finally, peek into the future of this whole process.
I mean, really think about it. It's something we do dozens, maybe hundreds of times a day without a second thought. But behind that simple physical click is a cascade of events that is anything but simple. We're about to see just how intricate this whole thing really is.
Okay, so let's start at the very beginning. Our journey kicks off with a physical action, you clicking a mouse. But how does a physical press of a button become something that a global network can understand? This is the first, and maybe one of the most fundamental steps, translating that action into digital language.
At its core, this whole thing is called data communication. Now, that sounds a bit formal, but think of it like the entire postal system. Your click, that's you writing a letter and dropping it in the mailbox. Data communication is the entire system, the trucks, the planes, the sorting facilities that make sure your letter gets where it's going. So here's the first bit of magic. Your click gets instantly translated into the native language of computers, binary. It becomes a unique stream of ones and zeros that says, hey, this person wants to see this web page. And just like that, this brand new digital message is officially ready to be sent out into the world. All right, our click is now a digital message. It's all encoded and ready to go, but it's still inside your house, digitally speaking. Its very first challenge is to navigate its immediate surroundings, your home or office network, and find the door to the outside world. This is your data's hometown, the local area network, or LAN for short. Just think about all the stuff connected to your Wi-Fi router, your phone, your laptop, maybe a smart TV, your gaming console. They're all neighbors living on the same LAN. Our little data packet's first job is to find the one exit out of this digital neighborhood, which is usually your router. And this is where the world starts to get a whole lot bigger for our little packet. It starts in the cozy, familiar land of your home, but it's about to step out onto the massive superhighway of the internet, a much, much vaster and more complex place. So once our data packet is out on the open road of the internet, it can't just wander around hoping for the best. Can you imagine millions of cars on a highway with no speed limits, no lanes, no traffic lights? It would be total chaos, right? Well, to prevent that exact kind of chaos, the internet runs on a very strict set of rules. And these rules are called protocols. I love this analogy, the grammar of the internet, because that's exactly what it is. If all this data zipping around is a global conversation, protocols are the shared language that make sure everyone can actually understand each other. Without them, the internet would just be noise. It is the absolute bedrock of how our digital world works. Okay, so let's think about this like we're shipping a package. It's basically an assembly line. First, the application layer writes the actual letter. That's your request. Then the transport layer chops that letter into smaller, numbered pages and puts them in an envelope so they can be reassembled later. Next, the network layer writes the full mailing address on the outside. And finally, the link layer slaps the right postage on it so it can get to the next post office. The point of all this wrapping and stamping is actually pretty genius. It guarantees that even if your request gets broken into a dozen tiny pieces that all take different routes to get there, they can all be put back together in the right order at the destination. It's an unbelievably resilient system. So our packet is all packaged up. It knows the rules of the road, but the internet is a massive place. We're talking billions of devices. How in the world does it find the one specific server it's looking for? You see, we type in easy-to-remember names like explainer.com, but computers don't think in words. They need numbers, specific numerical addresses. The system that acts as the translator between our world of words and the computer's world of numbers is called the Domain Name Service, or DNS. You can think of it as the internet's giant universal address book. Now, this whole process happens in a flash, but here's what's going on. Your computer basically shouts out to a DNS server, hey, what's the number for explainer.com? The DNS server quickly flips through its massive directory, finds the matching number, the IP address, and sends it right back. And boom, your data packet now has the exact coordinates for its destination. So let's just put these side by side to make it super clear. On the left, you've got the URL. That's for us, for the humans. It's easy to remember. On the right, you have the IP address. That's for the machines. It's a precise, unique address. And DNS is that critical translator that makes the two worlds talk to each other.
Okay, this journey is sounding pretty smooth so far, right? But let's not forget, the internet is a public space. It's not some private, secure tunnel. Our little data packet is traveling out in the open. And just like any trip, there are potential dangers along the way.
So what kind of dangers are we talking about? Well, someone could try to intercept the packet and read what's inside. They could even try to alter it while it's in transit. To guard against all this, we rely on an incredibly powerful tool, cryptography. There are two main ways to lock up data. Think of it like a lockbox. With a secret key, you have one single key that both locks and unlocks the box. It's fast, but you've got to figure out a safe way to give that key to the other person. Public key is way more clever. It gives everyone a public key, an open padlock, to lock the box, but only you have the unique private key that can open it. This is really the foundation of most security online. And this brings us to one of the coolest uses of this tech, the digital signature. You can think of this as the internet's official, tamper-proof wax seal on a letter. It guarantees two absolutely critical things. One, that the person who sent the message is who they say they are, and two, that the message hasn't been opened or changed one bit along the way.
So our data packet has made it. It's been unwrapped, reassembled, the website loads, and the journey is complete. All in a fraction of a second. But the roads it travels are changing constantly. New technologies are completely reshaping this entire process as we speak. The whole landscape is shifting. With cloud computing, our data might not even live in one specific place anymore. It could be spread across servers all over the world. Mobile IP makes sure we stay connected seamlessly as we move around. And then there's the really big one, the Internet of Things, or IoT, which is connecting literally everything to the web. And the scale of this change is it's mind-boggling. We're not talking about thousands or even millions of new devices here. We are talking about billions. Your smartwatch, your car, your doorbell, your fridge, every single one of them is starting its own tiny data journey, over and over, every single day.
So as our world gets more and more connected, the journey of a single click is only going to get more complex, more intertwined. And that leaves us with a really fascinating question to think about. When every single device is on the network, sending data on its own journey, what does the next click even look like?